So what's this graph all about? What's it telling you? It's got a line for halogen, it's got a line for 12-volt LED, it's got a line for 120-volt LED. So light, of course, is just a bunch of photons coming at you. And historically, we started bringing electric light to folks late 1800s or so. And almost right away, we came up with a way to dim it. This is actually in my house. These are solid state dimmers. So these are the dimmer part. This is the all on and the all off. And you see a whole bunch of different banks of these. And we've come a long way since then, because at the early days, what we would do is we would just, we had a big old piece of equipment that got hot. It basically dissipated the extra energy that wasn't used. Because if you're, to make a light work, you're bringing electrons in, you're bringing power in, and you're getting light out. And ostensibly, especially in the olden days, the more power you brought in, the more light came through. And conversely, the less power you brought in, the less light. So you could choke off the amount of light coming by choking off the amount of power. But back in the early days, we just diverted that power somewhere else. So there was no power savings. And actually, it was quite dangerous. People used to burn themselves. But it's the idea of a dimmer. It's a pretty straightforward idea. It's certainly one that you guys have used since you were children. There's all kinds of different flavors of dimmers, and some are circles and some are levers. These little ones, you've seen those before, right? Where you turn it on or off, but you kind of determine what fully on is by moving that up and down. And so what we're talking about here basically is actually fairly straightforward. It's not a very difficult question for some of you, but for some of you it is. So that we have a certain amount of power input, and we have a certain amount of light output for the amount of power that's coming in. And then everything between is depending on how we dim it. So in all three cases, if we have no power going in, we also have no light coming out. And in all three cases, if we have 100% of our rated power going in, we have essentially 100% of our rated light coming out. And the question is, what happens in between? And the answer is different depending on what type of light you have, what type of lamp you have. So the way that an incandescent lamp works is we have the power, the hot going in, and then the power goes across this little filament, which is like wired up, which is like curly hued up like that. And then it comes back through the neutral. And when that happens, there's some resistance here, and then it heats up. And when it heats up, it produces light. Now it also produces a lot of heat, a lot more heat than light. About 93% of the power goes to heating up the lamp, actually goes to heat, and only 7% goes to light. And dealing with that, kind of choking off the amount of light, dimming the amount of light in this type of bulb, this type of bulb is called an incandescent, which you probably know. But for an incandescent bulb, it's a pretty simple, simple, it's not super simple, it wasn't, but there's a fairly simple set of technologies that allow us to choke off the amount of power. And we're saving power, and we're also getting less light. So on the one hand, less power, but on the other hand, less light, which may be okay. If there's a glare or if there's daylight available, we'll get more into that in a little bit. Actually, we had only kind of complicated ways to do this until the mid 50s. And that's when a guy invented a smaller version of this that could just go in the light, go in the electrical box. I mean, in the light switch, just within the light switch. And that guy 2 years later went on to start Lutron. So Lutron as a company was very much started because of this technology. And then we moved into compact fluorescence. And now with compact fluorescence, and these are ballasted compact fluorescence because they have a ballast here, which means that we can screw it into an Edison socket, just a regular, household 120-volt socket. And we don't have to have the equipment to change, to regulate the current, because what happens in a fluorescent lamp is we have a tube here, and this tube has phosphors in it, and phosphors are like a little powder, and it's got a gas in it also, and we excite the gas, and the gas makes the phosphors light up, and that's what brings us the light in fluorescence. And in the case of ballasted compact fluorescence, compact because they're small, ballasted because they have this equipment here. This equipment allows the regular alternating 120-volt current to be transformed into exactly the type of current that we need. It regulates the current so that we can get a starting arc to get the thing going, and then get a maintaining one after it's going. And this guy uses like 1/6 as much power as the other one for the same amount of light. And there's a lot less heat going out too. So not only does it use much less power, but it requires our air conditioning system to work less hard, because we're not heating up our buildings with a bunch of easy bake ovens that are these incandescent lamps. And so these two are ballasted compact fluorescents. And of course, you guys know what these are. These are different flavors of LEDs. Some of them look more like old-fashioned light bulbs, and by old-fashioned, these are called A light bulbs, A-shaped, which actually stands for arbitrary, which is weird, but that's this kind of shape that we see that looks like this. And it's kind of like, well, it's like everything, right? Like when I was a kid, my grandmother had a TV, and the TV was like in a chest. It was like in a wooden piece of furniture, because we didn't know what TVs were supposed to look like. So we made them look like furniture, because that's the other stuff that we had in our house. And I had a simulated wood grain paneled station wagon. And that's because we didn't know what station wagons were supposed to look like. So we made them look like old-timey wooden trucks from like the 30s that had the wooden sides. And I kind of wonder right now what's going to happen with because I live in a college town, there are like there are motorized skateboards everywhere. Everyone's riding around on motorized skateboards, which again is the same thing. It's taking a motor, but it's putting it on the form of a product that we used before there was a motor. And so eventually the motor will change the fact that there is a motor will change the form of the skateboard, or maybe it won't. But it's kind of interesting and fun to think about. And I know there's lots of other type of scooters, but those don't seem to have taken off quite as much, at least in my town, as the motorized skateboard. So some of these look like light bulbs that we're used to because we're used to them, and people are maybe scared to buy something that looks like this, or were 10 years ago, maybe not so much anymore. But anyhow, this is a different technology altogether. And again, with a pretty small piece of equipment and nothing too difficult, we can also send power in here and out here, and we can dim it. Now, these use a piece of equipment called the driver, which is pretty much like a ballast for as far as we're concerned. As far as an engineer is concerned, there's different technology, but these use a driver, and the driver again kind of converts the alternating current into whatever LEDs, whatever type of flavor that particular LED wants to produce that particular color of light and so forth with that particular driver. So so we can dim these fairly easily as well, and we can go beyond this kind of all off and all on mode, and we can dim it. Now, halogens are a type of incandescent, so they're actually pretty much the same as these, only they have a filament that can get hotter, and they have a glass that can handle more heat, and they have a gas inside of here that can handle more heat, because that was Edison's genius. People had invented light bulbs before, but they always went out after a few seconds. But Edison put them in, put the filament inside of a vacuum, and that's what allowed it to last longer. And we can't keep it too hot with a traditional incandescent, but with a halogen, which is a type of incandescent. And I know that's confusing because a halogen, so we have something called incandescent, and then later we invent something called halogen, and that's also an incandescent, but the old type of incandescent is still just called incandescent. And the new type of incandescent is called halogen. So it's like the family name is incandescent, but within that we have incandescent, which is the old-fashioned ones, and we have halogen. And the reason we've kind of moved over to halogen, besides the fact that it's a whiter light that some people prefer, but it's also more efficient. It's about 30%, 25% more efficient. And so these days, just about any incandescent you would buy is actually a halogen. So when I say halogen, and again, we'll take a halogen, this is a halogen lamp, which is like a lamp is just a fancy way for a halogen light bulb. And we'll stick it inside of an arbitrary light bulb so that it looks familiar to us, and so that it's big enough so that we can plug it into we can screw it into an Edison screw. But it's just a halogen inside of a inside of a light bulb. And it looks, like I said, the light that comes off of it is a bit whiter and less yellow. It's cooler, which means it has a higher correlated color temperature. And so we have all these different types of light bulbs, and here's some LEDs, and here's a bunch of different shapes too. We have a G shape, which is a globe, and this again is a twisted ballasted compact fluorescent, and then we have this one does not have a ballast. Now, why would we not want to have a ballast on our compact fluorescent lamp? Go ahead and put your answer in the chat. Well, the reason we'd rather on a balance not have it in the lamp itself, and the lamp is the light bulb. The reason we'd rather not have it on the lamp is because we'd prefer to have it in the fixture. It's a piece of electronics, and so these guys that don't have a ballast are much cheaper to buy than these guys that do, because these guys that do have a piece of electronics that you're buying also, and that you're throwing away when it's done. So if we know we're going to have compact fluorescence in our fixtures anyway, instead of taking an Edison screw and screwing it in and then converting it with the throwaway equipment, we would rather buy cheaper versions of this and just put one ballast inside the fixture. So it's actually inside the equipment that's permanently part of the building. And then this one's a 4-pin. It's called a 4-pin. So we can plug it in with 4 pins. And when we relamp, it's not so expensive. So anyhow, we have parabolic aluminized reflectors. We have sodium lamps. We'll talk about that in a second. We have all kinds of different shapes. We have so many different choices. Almost an overwhelming number of choices is what we have. Now, aside from LED and compact fluorescent and incandescent halogen, we have a class of lights called high intensity discharge, HID. And these are the ones that produce a ton of light. We use them for stadia. We use them for parking lots and roads, or at least we used to before LEDs. And they take a long time to turn on, maybe 10 or 15 minutes to turn on. And they definitely can't, well, we can dim those, but they require, dimming an HID actually requires quite a bit of equipment, and it's not the kind of thing that can just be within the equipment of the light fixture or light switch itself. So, and they look like this. They're kind of like, it's in some ways they're like fluorescents, and actually fluorescents are called discharge lamps. These are high intensity discharge lamps, and there's a gas, and some of them look like they can screw in a traditional Edison screw, but they can't. I mean, you can screw it in, but nothing will happen. It doesn't light it up. You need to have the ballast that regulates the current to make sure the thing starts and ignites and then keeps going. And you see them high in the air often. There are 2 flavors of these that we're going to talk about. There's actually multiple flavors, but the one we looked at before, this one, is an HID lamp called a metal halide, and it's got a white look to it. And then this is something called a high pressure sodium, which has kind of the yellow look to it, which we're gradually kind of replacing high pressure sodiums with LEDs. And the reason we're doing it, not only because a lot of people prefer the look of the LEDs, and because your clothing and your skin look better under LED than they do under high pressure sodium, but we also do it because LEDs last a lot longer. And as you might imagine, it's pretty expensive to get a bucket truck out here and relamp these every 50,000 hours. We'd rather relamp them every, I don't know, 200,000 hours. That's a much better proposition. So, and LEDs, they used to not be really any more efficient than these guys, but we keep making progress on LEDs to the point where some of the LEDs are now more efficient, significantly more efficient than the other versions. So anyhow, so what we're talking about here is we're talking about a halogen. And so halogen starts at 0. And then as we add more and more power, you see, as we add more and more power, we don't get much more light at first. Then we start getting a lot more light, all the way up to where we're at 100% power, and then we get 100% light output. So that lets us know what's happening. Now with LEDs, it says we have 2 different flavors of LEDs. We have 120 volt, which does something like this, and we have 12 volt, which does something like this. Now, why would we need 2 different flavors of LEDs? Why do we need a 120 volt version and a 12-volt version? Or more specifically, when would you use one versus the other? Go ahead and put your answer in the chat. For those of you who are with us last week, remember that we talked about voltage being how much electrical pressure there was in the line. And so you could have a 9-volt battery, for instance, and you could put your finger across a 9-volt battery and you would not shock yourself. Now, if you put your tongue across both poles of a 9-volt battery, you will absolutely shock yourself. But if you put your finger across it, you won't, because there's not enough voltage in 9 volts, not enough electrical pressure, not enough oomph to push it into your skin and to go to the ground. So you generally will not get shocked if you have low voltage. And just like it is with 9 volt, same with a 12 volt. If we touch a 12 volt line, we're unlikely to get shocked. And even if we do get shocked, we're unlikely to get hurt. However, especially if we're standing in a puddle or something, if we touch a 120 volt line, you absolutely will get probably killed if you're standing in a puddle. And so what we want to do is, here we go. What we want to do is we want to, if we're going to be exposed to the, if we're going to potentially be exposed with our delicate little fingers to the wires, to the hot, in this case, the hot bars, the bars that have electrons running through them, then we need to make sure that it's low voltage, that it's something that won't hurt us. So track lighting, the beauty of track lighting is you have flexibility to kind of loosen this and slide it down to here. But in order to give us that flexibility on the inside of this, if we were to tuck our fingers into here, we would be the conductor, we would be the short connecting the hot to the neutral. So we don't want to be in that situation where people could put their fingers in here, and we want the electrons to go through the lamp and then back again, but we don't want a situation where our fingers are the thing that's actually arcing the electrons across between the hot and the neutral. So what we're going to do for track lighting is we're going to do it on low voltage. And someone said this also in the chat, if we have outdoor lighting and we're afraid of a short, or people are going to be outside in a puddle or something futzing with a light, we want to make sure we're using low voltage. This is my house, and these are, this is a cable track lighting, LEDs, and there's a transformer somewhere in the basement that takes that 120 volt. Remember, a transformer from last week, a transformer steps down the power from, in this case, 120 volts down to, say, 12 volts. I think this is 12 volt system, and maybe, yeah, I think it's 12 volt, maybe 24, but I think it's 12. And that way, if I am touching this wire and this wire, I'm unlikely to create a path that becomes a short circuit, because anytime you connect the hot to the neutral without going through a resistor that's intended to regulate, kind of throttle the amount of power going through it, then the whole thing heats up, and eventually you blow a fuse, hopefully, in best case scenario, and worst case scenario is you start a fire or electrocute someone. And so what we have is, well, we'll get to that in a little bit. So, well, I'll talk about it now. So we have lots of reasons to dim. Sometimes we dim for what's called daylight harvesting. So we'll have a photo sensor somewhere on the ceiling here. Maybe it's behind us, but somewhere on the ceiling, we'll have a photo sensor here, here, and here. And when there's enough light coming in through the window, we'll dim this zone of lights, and we'll off altogether. And then this one will dim a little bit, and this one will dim a lot. And here's a kind of a grainy picture also, where both of them are on here, but I think one of them is on here and one of them is on here. And so that way we're not producing more glare than we need. And also, importantly, we're limiting the amount of light we're using. And this is a really good idea. If you guys are designing office buildings, daylight harvesting is a great idea, because nobody ever gets up and turns off the light when the sun comes out and then turns it back on. Especially in these kind of open office plans, no one feels the authority, and if they do, they kind of piss off their neighbors. Who are they to go up and turn off the lights? So I'm a huge fan. I'm not generally a fan of overly automating things, but I am a huge fan of automation with photosensors that use daylight harvesting to, when the sun's out and there's enough light being provided by daylight, that we can throttle back the amount of electrons, the amount of power that we're going to be using, amount of energy that we're going to be using next to the windows. So let's take a look at this again. If we say at 40% power input, so we've throttled it to 40% of whatever the maximum is, with the halogen, you see we only get about 5% of the light. So we have 40% of the power input, but 5% of the light output. So it's probably not a great bargain in terms of energy savings and in terms of light output. With a 12-volt LED, and that's the kind that that goes outdoors or in places where you might touch it like a track light, at 40% power, we'll call it 30%. It's a little less than that, but we'll call it 30% of the light. So again, it's fairly linear, kind of, where it goes from 0 to 100, but it's not totally linear. And so we get to a point where we're at line voltage, which is the 120 volt LED, the kind where the wires are hidden and we can't have contact with them. And at 40% throttled down to 40% of the power input, we get 50% of the light, which seems like a pretty good deal. Now, aside from just energy savings from daylight harvesting, there are other reasons we might want to throttle down or dim the light. We may want to do it just as a way to save energy generally. So we may say, you know what, our power bills are pretty high and it doesn't seem like we need that much light. So let's dim everything by 10%. And, so by dimming by 10% of the light here, we can, so we're using 90% of the power to get about 90% of the light. So we can save energy. Now, as our electrical grid gets more sophisticated, and this is already starting to happen and has been actually happening for a while in commercial settings, when the power company really does not want to have brownouts, they don't want to turn off the power for customers, and the power company really does not want to build a new power plant to just to handle some peak load that's only going to happen a few hours a year. So what will happen, and what is happening now, is power companies are basically communicating with college campuses or hospital campuses or large office buildings and saying, we're about to raise your power rates for the next 3 afternoons because it's going to be really hot and we need that power to run everyone's air conditioning. So if you can cut your power bill by 10% over the next 3 afternoons, we, the power company, will give you a rebate, or that's a carrot version. Or if you don't cut yours by 10%, we, the power company, are going to charge you a significant surcharge of $15,000. And so what we can do centrally as these things become more solid state, as these dimming controls become more automated and more digital, we can actually talk to the power company and say, okay, we understand the next 3 afternoons power is going to be really, really scarce. So we're going to trim back our power usage on lighting by 40%. No one will even notice. We'll just do it gradually. No one will care. But for the next 3 afternoons, we're going to make it a little bit cooler. We're going to make it, a little bit darker inside of our office buildings, so that we don't get the surcharge, and so that the power company doesn't have to build another power plant. Because it turns out, well, why don't power companies want to build another power plant? It's not just because it's expensive to build another power plant, but what's the real friction with building a new power plant? Go ahead and put it in the chat. Oh man, it's the neighbors. People do not like when a power plant is erected near them. And for good reason. They spew out, if they're fossil fuel generators, they spew out particulates, and there's big power lines that people don't like those going across. So it makes a power company really unpopular. It ties them up in lawsuits for decades sometimes, while people are fighting to keep a power plant from opening up in their region or in their neighborhood. And so more than anything, the power company just would love to operate their existing plants, but not build a new one. They have no interest in building a new one. So if the takeaway for this is that if we throttle the power, we can throttle the light, but it's not completely linear. There are times where we throttle the power a little and get a tiny bit of light, and there are times when we throttle the power a little and get a lot of light. And it depends on the given lamp. All right. Good night. Get licensed. I'll see you guys next week.